Flip-flops and latches are fundamental building blocks in digital electronics, used primarily in the design of memory elements and sequential circuits. They are bistable devices, meaning they have two stable states which represent binary 0 and 1. These devices store a single bit of data and are crucial in designing circuits like registers, counters, and memory cells. Latches. A latch is a basic memory device that holds data based on the state of an input signal. It is level triggered, which means it is sensitive to the level, either high or low, of the control signal, often called the enable signal. When the enable signal is active, the latch captures and holds the input data. When the enable signal is inactive, the latch maintains its previous state, effectively latching the data. There are several types of latches, with the most common being the SR latch and the D latch. SR latch, set-reset latch. The SR latch is made of two cross-coupled NOR or NAND gates. It has two inputs, set S and reset R. When the set input is active, the latch stores a logic 1. When the reset input is active, the latch stores a logic 0. If both inputs are inactive, the latch holds its current state. One challenge with the SR latch is the invalid state, which occurs when both set and reset are active simultaneously. This state causes a conflict, making the output undefined. D-latch, data or delay latch. The D-latch is designed to overcome the invalid state issue in the SR latch. It has a single data input and an enable input. When the enable signal is active, the output follows the data input. When the enable signal is inactive, the latch holds its last state. This simplicity and reliability make the D-latch a common choice in digital circuits. Flip-flops. A flip-flop is similar to a latch, but with an essential difference. It is edge-triggered. This means that a flip-flop changes state only on the transition, rising or falling edge of the control signal, usually a clock pulse. This edge-triggered nature allows flip-flops to be more reliable and predictable in synchronous circuits. There are various types of flip-flops, each with specific characteristics and uses. SR flip-flop. The SR flip-flop is the clocked version of SR latch. It behaves similarly to the SR latch, but changes state only on the clock edge. This design eliminates issues related to simultaneous activation of set and reset inputs by ensuring changes occur only at the clock's edge. D flip-flop. The D flip-flop, like the D latch, has a single data input. However, it captures the input data only on the clock edge, either rising or falling. This design makes it ideal for storing and shifting data in synchronous circuits, as it ensures data is captured precisely at the clock pulse. JK flip-flop. The JK flip-flop is an enhancement of the SR flip-flop, designed to avoid the invalid state issue. It has two inputs, J and K, and a clock input. When J, A, and K are both high, the flip-flop toggles its state on the clock edge. If J is high and K is low, the flip-flop sets to 1. If J is low and K is high, the flip-flop resets to 0. If both are low, the state remains unchanged. T flip-flop? The T flip-flop, toggle flip-flop, is a simplified version of the JK flip-flop. It has a single input and a clock. When T is high, the flip-flop toggles its state on each clock pulse. When T is low, it holds its current state. T flip-flops are commonly used in counters, where toggling is required. Real-life use cases. Latches and flip-flops are used extensively in various digital devices and systems. Registers. Flip-flops are used in registers, which are small memory elements in CPUs that temporarily store data. For example, a D flip-flop can hold a single bit of data in a register until the next clock cycle, allowing for precise control of data flow within the CPU. Counters. T flip-flops are often used in digital counters. In devices like digital clocks, T flip-flops count pulses to keep track of time, toggling with each clock pulse to increment the count. Memory units. In random access memory, RAM, flip-flops store individual bits of data, allowing quick access and storage of information in computing systems. State machines. In digital systems, flip-flops and latches are used to build finite state machines, FSMs, that control the sequence of operations. For example, in an elevator control system, flip-flops manage the states of the elevator, like moving up, down, or stopping at a floor. Latches and flip-flops are integral to digital electronics, enabling the storage and control of data in various devices and systems. Latches are level triggered, making them simpler but more susceptible to issues in complex circuits. Flip-flops, being edge-triggered, provide greater reliability and are widely used in synchronous circuits like registers, counters, and memory units. Understanding these elements is key to designing efficient and effective digital systems, as they form the backbone of memory and sequential logic in modern electronics.